Hey everyone, in CS2107, one of the more interesting attacks covered is the padding oracle attack. It's not particularly easy to wrap your head around the attack at first, simply because there are quite a few moving parts, and the XOR operations involved don't exactly lend themselves to quick and easy interpretation. This video aims to provide an intuitive understanding and explanation for the mechanics behind the attack. The padding oracle attack really isn't that unapproachable once you break it down. The first part of this video will be dealing with the context and setup of the attack, while the second half will delve into the mechanics behind the attack. Now let's begin. What exactly is the padding oracle attack? Well, it provides a way for an attacker to retrieve the original plaintext from just the ciphertext alone. But this is a rather generic definition. A lot of attacks aim to do this. Instead, what really defines a padding oracle attack is the context in which it is set up, and there are four main parts to this context: the XOR operation, a block cipher using cipher block chaining or CBC mode, a padding standard, and last but not least, an oracle. Let's go through each of these parts in turn. Firstly, the XOR operation. Now, I'm sure most of you will be familiar with the XOR operation. It's a very simple bit operation that computers do all the time. I provided the XOR table in the top right hand corner over here for your reference. But there are two things about the XOR operation that are pertinent to our discussion today. The first is the fact that XOR operations are done bit by bit, byte by byte. What I mean by this is that if you XOR two sequences of bytes, as shown in this diagram over here, the output obtained is determined by comparing the bytes in each lane. Now, this might seem like a very obvious thing to most of you, but the point I'm driving towards is the fact that if I change one of the operand bytes, say the one right over here, only the bytes in this particular lane will be affected. All the other lanes remain unaffected. So this means that when we want to manipulate bytes in an XOR operation, we only need to focus our attention on the particular lane of interest. The XOR operation also has another peculiar property. Well, firstly, it's a binary operation, so it takes two operands and returns one result. So let's say we have A XOR B giving us C. That's a total of 2 plus 1 equals 3 entities involved, correct? Well, the thing about the XOR operation is that if you take any two of these three entities and you XOR them, you'll always get back the third entity. If you don't believe me, you can try it out for yourself. In this case, we can take B XOR to C to give us back A. We can also take A XOR to C to give us back B. This peculiar property of the XOR operation is repeatedly used when we try to understand and analyze the padding oracle attack. Next up, we have the block cipher. Let's focus on how block ciphers perform decryption. The encryption process is just the reverse of the decryption process, so I won't be spending much time on that. Block ciphers take a ciphertext as input, and it will break up this input into blocks of a certain fixed size. In my diagram over here, I broke up the ciphertext into 8 byte blocks, where each of these little squares over here represents 1 byte. Then, the block cipher proceeds to run a decryption algorithm on each of these blocks. The output plaintext blocks can then be concatenated to retrieve the original plaintext. Now, block ciphers have different modes of operation. One mode of operation that we're interested in is the CBC mode, or cipher block chaining mode. During the decryption process in CBC mode, the decrypted ciphertext block will also be XORed with the previous ciphertext block in order to retrieve the plaintext block. Now, this is quite a mouthful, so I personally prefer to just trace through the diagram. It's quite easy to understand such diagrams if you interpret all of these arrows as kind of like pipes for which all of these bytes can flow through. If we focus our attention on ciphertext block number 2 over here, which I've drawn to be 8 bytes long and I'm representing it in red, it will first be put through the block cipher decryption algorithm. Let's treat this algorithm as a black box. The actual algorithm and the implementation of it do not matter for the purposes of our discussion. After putting it through this particular black box, we get an output of 8 bytes as well. Note that this output will almost certainly be different from the initial ciphertext block, so I've drawn them in different colors, in this case blue. Then we'll be taking the previous ciphertext block, the one illustrated in green over here, and we'll be performing an XOR operation, giving us the plaintext block drawn here in yellow. Now, the same decryption process is repeated for each and every single ciphertext block. So when we perform an analysis, we can simply focus our attention to just this portion over here, because this entire portion is simply repeated again and again and again for all of the remaining blocks. Next up, we have the padding standard. Since we're using a block cipher, what happens when our input can't be nicely cut up into these same size blocks? In other words, what happens when our input size isn't an integer multiple of the block size? Such as this case here, where we only have 6 bytes in the last portion, which isn't enough to make an 8 byte block. The solution is very simple. We can simply add bytes at the end, padding it until we have enough bytes to form a full block. In this case, we'll just be adding 2 bytes. But the question remains, what should these two added bytes be? We can't possibly fill them up with random bytes, right? This is where the padding standard comes in. And there are many different padding standards out in existence, but we'll focus on PKCS number 7. And the idea behind PKCS number 7 is actually very simple. If you have to pad 1 byte, you pad it with 0, 1. If you have to pad 2 bytes, you pad it with 0, 2, 0, 2. If you have to pad 3 bytes, you pad it with 0, 3, 0, 3, 0, 3, and so on. I hope you get the idea. If the last block is full, meaning it has in our case a full 8 bytes, then we have to add an extra block of all zeros. Finally, we come to the last part of the context, the padding oracle. Now this is the most interesting mechanism involved. But actually an oracle is very, very simple. It's just a black box that answers a certain question. You give it some input and the oracle will answer yes or no depending on the question that it's designed to answer. In our case, we're going to use a padding oracle, where we give the oracle some ciphertext as input, and it will answer the question of whether or not the decrypted plain text has valid padding, according to the padding standard adopted. In our case, we'll be using PKCS number 7, as was mentioned 2 slides ago. Note this means that the padding oracle actually performs decryption. So it will know the secret key and which decryption algorithm to use. It's just that it doesn't reveal this key or anything else that is sensitive. It only reveals whether or not the decrypted plain text has valid padding. Nevertheless, it is important to recognize that the padding oracle itself is capable of and will perform decryption of the input ciphertext. So after all of this, we now have a good understanding of the context of the attack. But how does the attack actually happen? Let's focus our attention to a single unit of the decryption process. We've seen this diagram before, but let's first agree on some notation. We want to obtain the plain text corresponding to this ciphertext block. Let's call this C2. C2 will be put through the block cipher decryption algorithm, generating some kind of output. Let's call this output an intermediate state and label it I2. We need the previous ciphertext block as well. Let's call this C1. Now C1 will be XORed with I2 to give us the plain text block. Let's call that P2. Now for a very important fact. Since this block cipher is a deterministic algorithm, if we do not change C2, this means that I2 will also remain the same. In other words, if we keep C2, we don't ever change it, that means I2 will also be the same. Since we have the notation nailed down now, let's move forward and try to think like an attacker. The intuition behind the padding oracle attack is revealed when you ask yourself a couple of questions and make a couple of observations. Firstly, a yes from the padding oracle is more helpful than a no, because we actually know the format of the last few bytes of the plain text if it has a valid padding. It could be 01, it could be 0202, or it could be 030303, etc. We still have a couple of options, but it's a very limited subset. If it's a no, those last few bytes could literally be anything else. Next, as an attacker, we already have our hands on the ciphertext blocks. We can also control what ciphertext is provided as input to the padding oracle. Most importantly, we can change what ciphertext we input to the padding oracle. Lastly, by changing this ciphertext input, we can also change the decrypted plaintext that the padding oracle sees. So here's the key insight. We need to try and introduce some kind of change so that the padding oracle tells us the decrypted plaintext has valid padding. In other words, we can try to force the plaintext decrypted by the padding oracle to have some kind of desired valid padding by manipulating the ciphertext we provide as input to the padding oracle. Before we continue, I want to emphasize that we are dealing with two distinct scenarios here. The first is our original decryption scenario. Over here, we're dealing with the original ciphertext blocks and we never introduce any changes. But the thing is, we're stuck because we don't know the key for the ciphertext, but for the block cipher decryption algorithm over here. So we can't find the plain text. The second scenario we're dealing with is the padding oracle scenario, which, as we've mentioned a couple of slides ago, is fully capable of performing decryption on the input ciphertext. We want to introduce some kind of change in this padding oracle scenario over here. But what kind of change should we introduce? So here is the crux of the attack. We're going to change C1, and we're going to leave C2 unchanged as compared to the original decryption scenario. And as I mentioned just now, if we leave C2 unchanged, and since the block cipher decryption algorithm is deterministic, this means that I2 will also remain unchanged as well, as compared to the original decryption scenario on the right hand side over here. So let's focus our attention on the padding oracle scenario first. For starters, let's try and force the very last byte of the plaintext to be 01, and the thing is, this is valid padding. And in the original scenario, the plaintext wouldn't have been decrypted to become 01, but we're trying to force the plaintext decrypted to have a 01 as its last byte. And we're going to achieve this by introducing some kind of change to C1 while keeping C2 unchanged. So let's label the last byte of I2 as X1. Remember, we kept C2 in its original form when providing the ciphertext blocks as input to the padding oracle. Since C2 remains unchanged, that means that X1 remains unchanged as well. But it's just that we don't know its value. Then we're going to try and change C1. We only need to change the last byte of C1 since we're only trying to change the last byte of the plaintext to become 01. So let's call this last byte of C1 T1. But the thing is, what should we change this value of T1 to? This is where an exhaustive search comes in. And you have to recognize that T1 is only 1 byte long. So it can only take on values from 0 to 255 or 00 to FF for those of you who prefer hexadecimals instead. So we only need a simple for loop, looping through and searching through 0 to 255 for the last byte. And when the padding oracle finally outputs yes, then we'll know what value T1 needs to be. At this point in time, we'll know the value of T1. We also know the value of the last byte of P2 because we're forcing it to become 01. And then we note that this is an XOR operation. As I mentioned just now, for an XOR operation, if you know two of the entities, you can simply XOR them together to retrieve the last entity. Therefore, we can now find out the value of X1. Initially, we didn't know this. It's an unknown value. But now, through this process, we're able to find out the value of X1. We just need to XOR T1 together with the value 01. Now, let's swap back to our original scenario where we didn't change the ciphertext. Our aim is to find the last byte of the original plaintext, the one indicated in purple right over here. We have our hands on all of the ciphertext blocks, so that means we know the last byte of the original ciphertext block C1. On the previous slide, we also found the last byte of the intermediate state X1, of the intermediate state I2, and this particular last byte will be X1. Once again, we have an XOR operation over here. We know X1, C1, as well as X1 over here. So we can just XOR these two things together to get us P1. And just like that, we found the last byte of the plaintext. From now onwards, we just need to repeat this process for the rest of the bytes, moving from right to left. Just to make things clear, I'll go through how to obtain the second last byte of the plaintext as well. Back to the padding oracle scenario. We now want to force the plaintext to have 0202 for the padding, which is valid padding according to the PKCS number 7 standard. Once again, we're going to keep C2 unchanged and make changes to C1. We're only concerned with the last two bytes of the intermediate state. Let's label them as X1 and X2. We already found the value of X1, as was covered in the previous two slides. For X2, we don't know its exact value, but we know that since we didn't change C2, that means I2 remains unchanged as well. So X2 will also remain unchanged. In other words, it's unknown. Its value is unknown, but we know that it's unchanged. Let's also label the last two bytes of C1 as T2 and T1 respectively. Let's focus our attention on just the XOR operation involving all of these last two bytes. Over in this diagram over here. Since we have both X1 and 02, we can easily find the value of T1 by XORing X1 and 02. So just like that, we know the value of T1. Now the question is, what should T2 be? This is where, similar to what was covered 2 slides ago, we have to conduct an exhaustive search. T2 can only take on values from 0 to 255. We just do a simple for loop, and the moment the padding oracle outputs yes, we'll know what the value of T2 should be. Now, we know the value of T2. We also know the value 02 over here. We have two entities, so we can simply XOR 02 with T2 to obtain the value of X2. Now, back to the original decryption context. We already know the last byte of the plaintext, so we're not interested in the last bytes of this ciphertext block or the intermediate state. We are interested in finding out the second last byte of the plaintext. So if we have our hands on the original ciphertext blocks, we know the second last byte of C1 over here. We also found on the previous slide the value of the second last byte of I2, which is X2. we found the value of x2 on the previous slide. Once again, this is an XOR operation. So in order to retrieve the second last byte of the plain text over here, we simply need to XOR C2 with x2. And just like that, through these past couple of slides, we have managed to find out the last 2 bytes of the original plain text. In order to find out the rest of the bytes of the plain text, we just need to repeat this process for the rest of the blocks. I hope you guys get the idea by now. Ultimately, the padding oracle attack is meant to illustrate the idea that something as innocuous as revealing whether the padding is valid, when abused in the right context, can reveal a lot of information. I hope you found this video helpful. Thank you.